This class is for 4.1 analog IC design. So in this online class, we are supposed to have few students to attend, but nobody has attended yet. But I will just record it so that in future student can go through this video. So we are going to discuss today about switching circuit, switching capacitance circuit, switch capacitor circuit, SC circuit. So in the beginning, I will do some overview regarding integrator and differentiator as we have used before with the RC active resistance and capacitance, how they work, and then I'll move to the integrator and differentiator design with the switch capacitor. So, and we'll explain why we use switch capacitor instead of resistor, and also using this switch capacitor we'll do some different topology about integrator and unit gain buffer. And finally, we'll show how to generate non-overlap clock, sample clock to switch the capacitance. And then finally, we'll see the switching circuit, switching MOSFET used as a switching purpose. What is the advantage, disadvantage using MOS as a switching circuit. So the overview, we use op-amp to have inverting amplifier and non-inverting amplifier. So the inverting amplifier, the power supply is in the negative node, and then the positive node is connected to the ground. And then the output voltage V0 is equals to RF by RI, supply voltage. RF is the feedback resistance, RI is the input resistance. In this circuit, we did not use any capacitance. We use only resistance. And here also the other topology. Here the supply also connected to the negative pole, and that's why the V out equals to minus RF by RI into supply. But the non-inverting amplifier, the supply is in the positive node, and then the output is positive value. V out equals to 1 plus RF by RI of the supply. And if we do it in this way, the polarity of the supply is changed, then the V out will be 1 plus RF by RI EI from the supply. A unit buffer, in unit buffer we don't have any resistance, no RI, no RF. That means RI and RF both equals to 0. So if we put that RF and RF value, then V0 becomes EI, so supply voltage. So it's called buffer. The output is equals to the input voltage. Now the integrator. These are going to be the real focus for our study today. With the active resistance, we design integrator like this. The RF is replaced with the C2, and then the V out by V in equals to RF over RI. So RI is in the bottom, and RF equals to inverse of C. That's why V out by V in equals to minus 1 over Ri into SC2 or j omega C2 Ri. For the differentiator, the capacity Ri is replaced with this C1 and then the RF is R. So here also RF divided by Ri, Ri is SC1. So the V out by V in equals to SC1 R. The R is equals to RF. Or we can write with the frequency response minus j omega C1 R. So why we replace the resistance with the capacitance in the analog IC design? The manufacturing of capacitance is more easier and also accurate than the manufacturing or fabrication of resistance. So how we make the capacitance? We just fabricate a transistor, MOSFET transistor, and then connect the source and drain together. Then it becomes a capacitor. This gate is the one terminal of the capacitor, and then the source and drain is the another terminal of the capacitor. So this transistor acts as a capacitor. So if you see in a three-dimensional view or the cross-section view, the source and drain is connected to the B point and gate is to the A point. So the gate and the gate oxide here acts as a capacitor. Also we can design with the metal capacitor, like make a one plate of metal B, on top of it make another plate or metal layer on top of it, which is A. So B is on top of A is on top of B. Between B and A there is oxide. So if we look into the cross-section view, this is the B, and then top metal is the A, which is connected to this contact. B is connected to this contact, and between A and B is the oxide. So it acts as a two plate in between oxide layer. And the C, the capacitance of this A and this type of capacitor is given C equal to epsilon oxide divided by oxide thickness into the area. How do we make resistance in the IC? There are four types of resistance: poly resistance, fuel resistance, diffusion resistance, and implantation resistance. The diffusion resistance is like in the POL, we make a diffusion layer, and then the two corner of the diffusion layer, we bring out the contact A and B, and this two is the two terminal of the resistance, and the amount of resistance depends on the n plus diffusion resistance. N plus diffusion resistance makes the total resistance from A to B. And in the top view is like this. In the POL we make a long thin layer of diffusion of n plus, and this acts as the resistance. Similarly with the poly, so the instead of that place we did the diffusion, we can make polysilicon layer on top of a layer of oxide. This is the substrate. This white part is the substrate. On top of substrate is oxide. On top of oxide is the poly layer, polysilicon layer, and its two terminal acts as a resistance terminal. So in the P well, also we can use as a resistance. So we make the P well, and then the two terminal of the P well, we consider the two terminal of the resistance, and the P well resistance The resistance of this PL acts as a resistance of AB terminal. Now, how to calculate the resistance? Here you can easily understand. Usually, since the layers are very thin, so we don't go to the thickness of the layer. We just go by the surface of the layer. So in the surface, we divide the layer into several square. So here, this is the resistance, and this two side is the contact. So this resistance we divide into several square. 1, 2, 3, 4, 5, 6, 7, 8 layer here. So if per square has 100 ohm, so this resistance will be 8 times 100 plus the contact resistance. This contact and this contact. So the total resistance is 8 into 100 plus contact resistance. So I have another resistance like this. So we make into square like this. So here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of them like this. And then we have a not regular square here. So then we break this part into several new square. A, B, C, another new square. So this 10 of them is parallel. So 1 to 5 will be 5 square. So it is 5 into 100. And 8 to 10 will be another 500. So these two are parallel. This one and this one is parallel. So this the equivalent resistance will be 1 over 500 plus 1 over 500, which is 250. And for ABC, these are three parallel. So it will be 1 over 100 plus 1 over 100 plus 1 over 100 because each square is 100. So it will be 3 over 100. So the total resistance will be 250 plus 3.3, 33.3. So 283.3 ohm. So that's how we calculate the resistance. Now we see how we can use the capacitance. So the capacitance is more accurate and easy to manufacture. That's why we will replace resistance with the capacitance. So in the integrator, we have one resistance and one capacitance. So we will keep the capacitance there, but we will change the resistance, we take capacitance. So how we act a capacitor as a resistor. Here, there is two supply VA and VB across resistance R, point A and B. So this one is done replacing this resistance with a capacitor connected to the ground, adding two switches, S1 and S2. This S1 and S2 switches work in two phases. When S1 is on, S2 will be off. When S2 is off, S1 will be on. So here, if you clearly try to look into it, when S1 is on, S2 is off. S1 is on, S2 is off, then it will be charging. Capacitance C will be charging. When S1 is off and S2 is on, then it will be discharging. So this charging and discharging will move the electrons from VA to VB, or from A terminal to B terminal. What the resistance does, the current flows from A to B. So here also the charging and discharging making the flow of current from A to B. So let us consider the switches. We will use the MOSFET as a switch to make this resistance out of switch capacitor. So in previous circuit where we have the integrator, so in the integrator we had a resistance here, and then the capacitor here, C2 is there. We don't want to replace C2, but the resistance here, after the in to VG, virtual ground, we replace it with this switch capacitor. And we added two MOSFET to control the switching. So this MOSFET is controlled by phi 1 clock, and this MOSFET is by phi 2 clock. Remember, this phi 1, phi 2 are non-overlapping clock, and this is faster than the input signal. The frequency of input signal is way below than the frequency of sampling clock. Phi 1, phi 2 is a sampling clock. So the phi 1, phi 2, if we draw the graphical representation of phi 1, phi 2, when phi 1 is on, phi 2 is off, and when phi 2 is on, phi 1 is off. So how do you make this? If you go 2 pages later, you'll see that here, what do? We take the clock and then send the clock to a phi 1 through an inverter. So the clock here is one inverter, here is one inverter. So phi 1 is same phase as clock, and phi 2 is opposite phase of clock. And to make the delay equal, so we add a resistance pass gate here, PMOS and NMOS. PMOS is always on here, and NMOS also always on here, but it acts as a resistance so that the delay from this point to the phi 1 and from this point to the phi 2 is same, but it will create opposite clock. Here, to make it non-overlapping, so we do the feedback. As long as phi 1 is on, it will be off. And when phi 1 gets off, then it will be on. And when phi 1 gets off, then it will be on. So there will be no overlapping. That means both of them are on at the same time. So let's back where we are discussing. Here, so we apply that two phase phi 1 and phi 2 across C1. Across C1, we replace the resistance with C1. So when the phi 1 is on and phi 2 is off, then the circuit look like this. So it is charging. And when the phi 1 is off and phi 1 is on, then the circuit looks like this. Then means this is discharging. So the in one cycle, C1 charges, another cycle C1 discharges. That means the current is flowing from Vi to virtual ground all the way to Vout. So let us consider that amount of charge that transfer. It depends on the V in and then the C1, Q equal to CV. So the amount of charge every time we take sample, this amount of charge move from voltage source to the C1. So average current flow between in and virtual ground, that is between in and virtual ground. If it is IA, and then I equals to C1 V in divided by the sampling time, switching speed. It is so short that it shows as continuous. So how about Ri? Ri equals to V in divided by I average. And then I average we found from this new circuit is this. So if we put the I average here, then R1 equals to this. So that the relation between the C and R is this. It depends on the sampling frequency and the capacitor size. The higher the capacitor size, the lower the resistance. So if we need a bigger resistance, then we need a smaller capacitance. And also we can change the sampling frequency. Changing the sampling frequency also we can make the adjustment of the resistance. So if the higher the resistance, we need the higher frequency, what is called lower frequency sampling. T should be bigger, that means frequency is smaller. So R1C2 is the time constant. In the integrator, if you see in the first here, we need RIC2. RIC2, we keep the C2 here and we replace RI with the C1. So RIC2 will be Ri will be Tc by C1, Tc by C1 into C2, C2 by C2 Tc. This is the time constant. So the V0 will be this. So it depends on the C1 and C2. There is no R. So since the fabrication of capacitance is easier and accurate, so our analog IC integrator, we can use only capacitance and then make this integrator. And here is the different topology of that integrator. So this is the resistance we replaced over there. On that place, the C1 was connected to ground. Since the C1 connected to ground, charging and discharging of C1 is not 100%. So we replace that C1 like this. And then the switching we are doing with this four transistor. We need more transistor here to make it more accurate and better. So this phi 1 and phi 1 switch on together, and phi 2 and phi 2 switch on together. They are non-overlapped clock or sampling clock. So how does it work? So M1, M2, M1, this is M1, this is M2, this is M3, and this is M4. So M1, M2 on, that means phi 1, phi 2 on, M3, M4 off, C1 charging by V in. So it charges the C1, while C2 hold the previous value, and this one hold the previous value because this one is off. And then M1 and M2 off, then next cycle we make it off and then we open it. So when you off it, then C1 is not losing anything because it is not connected straight to the ground. So then the second time M3 and M4 on. So the capacitance charge here. Actually what happened is C1 discharge this way. That means C1 is going down, and then since the inverter is negative non-inverting inverter, just like this part, it will be positive. Here it is going down, means it's lowering the supply voltage. So it will be increasing the supply voltage. So it will become a non-inverting inverter. So this on integration, this is in integration mode, charge C1 transfer from C1 to C2, and C2 hold the additional charge. So this way it accumulates the charge and it goes higher and it becomes a positive charge holder, and then this integrator acts like a non-inverting integrator. Another topology is like this. Here also we need 4 transistors, but here phi 1 and phi 2 is there in M1 and M2, and phi 2 is in the M3 and M4. So what will happen once we open phi 1 and phi 1, then it's charge C1 as well as transfer the charge to C2. So this is charging or sampling and integration together. And then we turn off phi 1 and turn on phi 2. And when we turn on phi 2, the C1, both sides will discharge, and it will not have additional or extra or stray capacitance or stray charge accumulated in C1. So which is not from Vi. So it will be this C1 will be chargeless C1. The next time when we will take the sampling, we will get the exact V in here, and then that V in will transfer to C2. So this way this uh, will be more accurate according to the Vin, because the every other after the sampling, next time after the sampling we discharge the both side of C1, so there will be no stray charge or stray capacitance, parasitic capacitance there. So this is so far we talk about integrator. Here actually we are going to discuss about unit buffer. Before we go to unit buffer, we want to explain why the unit buffer is not non-inverting. Now is non-inverting. Why it is not inverting? Here we explaining with this amplifier. Here we have a C1 and C2, and there are 3 transistors for switching purpose. This 2 is the phi 1 for charging and amplification, and phi 2 is for discharging. So M1 and M2, M1 and M2 on, M3 is off, so C1 charge. So it will charge, the point P will be charging from V in, so it will charging. So this will go from 0 to V in, 0 to V in. So here is the graph here. This Vp goes from 0 to V in. This axis is Vp, and this is time. So the Vp initial will be, in the first in first mode when M1 and M2 is on and M3 is off, then the Vp value will be V. So after a while, the end of the sampling, M2 off before M1 off. What is this? This M2 is off before M1. Then the transistor get off, and then this one. So when this transistor get off, then the current flows through this T2. So some charge come over here. So the C1, so that it does not lose much charge, that's why the V in is connected here. And then after a while, then F1 is, I mean the M1 is turned off. So even though some charge move to C2, but the C1 remain, that charge is according to V in. So the point P, it was a V in, and when M1 off, then this goes down a little bit. The M1 is this one, okay. So that this goes down a little bit. This charge went to the capacitor C, and when we open the M3, when you open M3, then the charge from P discharge to the ground. Charge from P discharge to the ground. So Vp becomes 0. So when Vp becomes 0, that means the point P is going from V in to 0. And this topology is in inverting mode. So since it is going V into 0, P is going V into 0. So the V out will going to 0 to this. So it will be increasing. So as it is going down, it is increasing. So V in also increasing, V out also is increasing. That's why it is non-inverting topology. This is non-inverting amplifier. So we use this topology for unit gain buffer circuit. Buffer circuit is unit gain circuit is like this. The supply is given from here to the positive end. So V in straight come here, and then we get the output V out also equals to V in. Now we don't have any resistance. So how do you do the sampling then? So what we'll do, we'll add a capacitance here in the feedback, and also another capacitance here. So this capacitor will be doing for the sampling, and this capacitor will be act as a integrator, or as a it will be act as an integrator. But this capacitance and this capacitance, these two, in the integrator, one is C2, another is C1. But here we will use both capacitance same. So the V out will be C1 by C2 V in, which is CH by CH V in, which is V in. So it will be like a unit gain. So let's see the topology here. So here CH, here also CH. So in sampling, it will charge this C1 CH and then the discharge the CH. So the CH over CH, it will cancel each other. So whatever charge it will come from V in, the whole thing will go to V out. So it will act as a buffer. It has another topology also. This one here, in that case we use two capacitors. Here we using a single capacitor or multiple switch. So what happened in the sampling, M3 off, this one is off. So M2 and M1 is on. So it will look like this. So it will be charging. And the next will make the M3 on and M2 and M1 off. So when this one is off and this one is off, then this terminal is going to V out. That means looks like a feedback. So the same capacitor is act like a sampling, also act like a feedback. So it is the same capacitance, that's why it's CH over CH, CH sample, CH hold. So the output is equal to input. It's a buffer. Another way is doing this. Best way of sampling M2 off before M1 off. So like this one, M2 off before M1 off. M2 off before M1 off. So if it is disconnected first and then this one, then this charge will stay here. It doesn't go to the V out. But when it goes to the integration mode, it will move to the V out. And this one I already discussed how to generate non-overlap two-phase clock from a single clock. Now we are going to see the characteristics of a MOSFET using as a switch. So when we excuse me, when you use a MOSFET between A and B as a switch, the phi is the switching clock. So phi is either 0 or 1. So when it is 0, then the MOSFET is off. There will be no current flowing from A to B. But when phi is on, that means 1, and then from A to B, there will be a current flow. So since phi is 1, but the A and B is not as high as like phi. It has a potential difference between A and B, but that difference is not as much as the 1, the phi, when it is 1. So that's why the VDS, if it is the in this MOSFET, if one is source, another is drain, and the voltage across A and B is VDS, and this VDS is very small. So the VDS is very small compared to the gate voltage. The small VDS is small and VGS is high, large. So that's why it's in a linear mode, not in saturation mode. So the current flow across AB is given by linear current. VDS is between 0 and VGS minus VT. So since VDS is very small, the square of VDS we can ignore it. So it will be, IG will be proportional to VDS. So the resistance will be V by I. VDS by ID equals to resistance, which is like 1 over this, 1 over this L will go up and these things will go down. So this is the resistance of that transistor when it is act as a switch. And here we draw the curve. VDS increases, I also increases, and VDS linear to I, VDS linear to I. So that's why it is VDS linear to I. It's linear. If VGS 1 and VGS 2, VGS 2 greater than VGS 1, I mean the gate voltage instead, if the gate voltage is higher, the characteristic curve becomes steeper. Gate voltage is lower, the characteristic becomes slower. And when the VGS equals to VT, there will be no current. When VGS equals to VT, I will be 0. So here the I is 0 when VGS is VT. So actually the curve will be like this from here to here, and we can interpolate it in the negative current. So depending on the VGS and VDS, current either flow this way or flow this way. Now, what is the problem in the MOSFET switch? The biggest problem is called clock feed through. Clock feed through. What is called clock feed through? This transistor we are using as a switch. So when this transistor on, then the current from V in goes to the capacitor. And as long as this transistor is off, no current will go from V in to capacitor. But voltage in the gate of this transistor, if we gradually increase, and as long as it's lower than VT, it will be off. And then since it is a high frequency sample clock, so it will go from 0 to 1 or V1. So as soon as it will go from 0 to 1 or 0 to V1, in the beginning it will be off, so no current, no charge will move from V into C1. But in the beginning, since it is quickly moving from 0 to V1, because the V in frequency is way smaller than F1 frequency. So as soon as the F1 goes to V1, the charge from gate to the C1 through VGD, if it is the drain and if it is the source, and the VGD, the parasitic capacitance of this transistor, will send charge to the C1. So this is the call feed through. As it's not coming from V in, it's coming from the clock. So we don't want that, because we want the signal to be exactly to the C1, not from the clock. So here it is saying this: if phi1 is greater than Vt, it is charges by V in. But if phi1 is less than Vt, then it charges from phi1 to C1. So what do we do? How to eliminate this extra charge because of this feed through? Use minimum size of MOSFET. So if the size of the MOSFET is smaller, the CGD, gate to drain capacitance, is almost small, like a 0. So it will not have any effect. So there's a smaller transistor is a one option. Another is a dummy transistor with an opposite feed through. So what will happen if we have this is the real transistor with the phi1 clock. So we'll make another transistor here, which will be turned on with the phi1 bar. So when it is giving positive charge here, it will be giving negative charge here. So these two charges will be neutralizing it will not go to C1. Like Q equal to CV, phi 1 into CGD1 minus phi 1 into CGD2 M2 GD2. So these two is opposite, so becomes 0. So another thing is a dummy transistor using transistor. So we need an extra transistor. So for each switch we need 2 transistors. So if there is 3 switching arrangement, then we need a 6 transistor. But we can this way we can use any transistor. Otherwise we need to make minimum size transistor. Another is small clock swing, which is the V1 is small. So with the smaller voltage we can turn on this one. So if V1 is small, then very small amount of charge will come here, because the Q equal to CV. If the V1 is small, then a very small charge will come here, which will be very negligible compared to the V in, what the V in sending here. So the fifth row we can excuse me, we can manage by minimum size transistor with the dummy transistor or small clock swing. Now more explanation about this transistor switch. If the V in is smaller than, way smaller than V1, then output voltage is V out. We can get exactly V in, because VGS minus VT greater than VDS, and it is in such a linear region, so it will gradually charge and then it will reach V in, since V in is less than V1. So the V in is high, VGS minus VT will be greater than VDS. If the V in and the V1 is same, if the V in and V1 is same, then M1 in saturation. If M1 is saturation, we get this relation, and from this relation if we integrate, we will get maximum V out. Maximum V out will be V1 minus VT. Though we are sending V in, so the V in will be increasing gradually, and it will increase up to V1 minus VT, because V in and V1 are equal. So if the clock high and then the input high is same, then we can go maximum to V in or V1 minus VT. But to use this transistor properly, so that we can get the output voltage according to the input voltage, we need to use the MOSFET, that complementary switch. We need to use complementary switch, both N and P, because the N can pass 0, good 0, P can pass good 1. So both of them combinedly will be passing V in to V out, no matter what is the phi, maximum phi, what is the value of the V1. So the resistance will be almost like uniform. So this one is the on for the NMOS, and this part is on for the PMOS. So after that, PMOS is infinite resistance. After that, NMOS is infinite resistance. So the NMOS can transfer from V1 minus VT, but the PMOS will transfer further. So this V1 minus VT, we can go beyond this, because the resistance, combined resistance of this is way below the NMOS resistance. Here NMOS resistance is so high that it cannot go more than this, V1 minus VT. So this way we can use complementary switch like this. But the problem is that if I need 3 switches, I need 6 of them, as well as for each one we need a dummy transistor. So 4 transistors combined make 1 switch. So it's more expensive but more accurate. So for the switching capacitance, that's all we had. So I hope you will understand all the lecture. Hopefully when we meet in the class, then we may go through these things again very quick. And if you understand uh, by hearing my lecture, video lecture, then we don't have to go through it. So, or if you have any few questions regarding it, we may discuss on this in the class. So for now today, we're going to close the class here. Thank you for listening, and we'll come again next Thursday for analog IC next class, online next class. Hopefully we'll be done with the first class by that time, and we can go for the second class. Thank you all.